In this ProteusDS training session, we're going to talk about fundamentals and working with the rigid body D object. We're going to cover mass properties, working with the rigid body and the rigid body reference frame, and we're going to spend a lot of time talking about hydrodynamic features for the rigid body. Alright, there's a few input files to follow along with that are downloadable separate from the tutorial videos. RigidBody and EcoSpray both hold sample projects, and just double click on the PDS file to open them. We don't have to do that just yet. So why would we use a rigid body model? What's the point? Well, rigid bodies have what's different about a rigid body compared to the other models in the software, like point mass or X masses, like you see in the spherical float in the background, is the orientation. And orientation can come into play when you've got larger structures or oddly shaped structures like this boat hull shaped buoy. This is called a nomad buoy. And it's quite sizable as well, but because of its shape, it often it's nice to be able to use a lot of custom features here to give to allow the definition of the hull play into the hydrodynamic loading. In addition, because they're bigger, and often there's a lot more detail that's needed in the orientation of how the pitch and roll of the buoy changes through the course of a simulation. And that's what the rigid body model is good for. So when we talk about the degrees of freedom, DOF, degrees of freedom, a rigid body has 6. There's the linear ones, just like the point mass has surge, sway, and heave. These are the linear positions X, Y, and Z. And then there's also the orientations, roll, pitch, and yaw, which is rotation about X and Y and Z. What's crucial to understand when working with rigid bodies is how the rigid body reference frame works. All rigid bodies have a rigid body reference frame. The rigid body reference frame, in fact, that describes the state of the system, how the rigid body frame has moved away in position and orientation from the global frame is the state of the rigid body. And so when we want to configure a rigid body model with a lot of details, what you're really doing is specifying the information that about the rigid body with respect to that rigid body reference frame. This means that how you set up your model and where the rigid body reference frame is arbitrary. So it's really important to consider picking a location that's invariant to design and easy to measure connections and features from. So like in this example with this nomad buoy, everything is configured such that the rigid body reference frame is at the baseline and at the aft of the buoy. We also, for vehicles and shaped structures and things like that, we will often set up with the rigid body X frame pointing positive forward. And when you do that, it means the orientations of the rigid body frame, roll, pitch, and yaw, correspond to the roll, pitch, and yaw of the platform. So when we talk about specifying things like the center of gravity location, you would be specifying an X position in terms of the X frame, this local rigid body frame, and the Z position, something like that would be about where the center of gravity for this nomad buoy would be. There might be more mooring connections off to the side and up in an elevation here. So, that 3D configuration and a lot of is really nice and crucial for working with the rigid body model. And then these parameters are expressed within the rigid body reference frame, which are constants throughout the simulation. These deflections, these positions don't change, even though the rigid body model is moving through the environmental domain. So some fundamental parameters are the mass of the rigid body, but this also means the inertia properties as well, mass, moments, and products of inertia, the center of gravity location. These are pretty much fundamental properties. Be aware there's more than one way to specify the inertia. You could define the inertia about the CG location, but it's also possible to specify the inertia properties with respect to the rigid body frame. And this is kind of handy if you're working with a CAD program that can tell you the inertia properties expressed at different points on the system. Okay, now we're going to talk about hydrodynamic features. there's many different kinds of hydrodynamic features for a rigid body. When you create a rigid body in Proteus Simulation Toolbox, you'll note that here's the visualizer showing our empty world. When I create a rigid body, here's the mass and inertia properties, but that little gray and the white and black ball is the center of gravity of the rigid body. It doesn't have any hull. There's no physical presence. And so that's why we get into working with these hydrodynamic features. There's a lot of different built-in parametric types like cylinder, cuboid, ellipsoid as well. You can import a custom hull file. Each feature has its local feature frame. And the way that you configure these and add these hydrodynamic features to the rigid body is a key aspect of them is specifying the feature frame, location, and orientation with respect to the rigid body reference frame. Let's talk about the hydrodynamic cylinder feature. The hydrodynamic cylinder feature is based on a Morrison loading approach, so it's calculating drag, it's calculating added mass, and incident wave loading, Krylov loading, and buoyancy loads, but it's not doing anything with wave radiation and diffraction, and that's a topic for advanced hydrodynamics. This is what you might see when you configure a basic cylinder. There's some key parameters, of course the length and diameter. You can specify the normal and axial drag and added mass coefficients, and there's several automatic mesh inputs, angular, radial, and axial. So what's nice about this is while you're configuring your files in ProteusDS Simulation Toolbox, you can adjust the number of polygons you have in here. And of course there's trade-offs with computational efficiency and speed if you add more polygons. So in this case, the feature frame is the cylinder frame has X and Y coordinates in the cross-section plane of the cylinder and Z along the axis of the cylinder. And the feature frame is always halfway through the middle of the cylinder, mid-span. So again, specifying this when you want to add a cylinder, what you're really doing is telling the software in the inputs how has this feature frame, the cylinder frame, moved away from the rigid body frame. Now, if we had a rigid body frame here, there's our global frame, rigid body frame here, and we have these 6 inputs. These are the linear offsets, X, Y, Z, and then the rotation offsets, roll, pitch, yaw. With only a -5, that's going to move the cylinder frame up here, the length of the cylinder offset by that much from the rigid body frame. That's what it might look like in post-PDS. It's your basic cylinder. Now you can add 2 cylinders, and we've added a bit more complexity here where we've given, in addition to the Z offset, we've got 1 cylinder with a positive Y offset in terms of the rigid body frame, and another one with a negative Y offset in terms of the rigid body frame, and then 0 roll but 90 degrees pitch for these 2 hulls here. This might be a good time to bring up the sample input files here. So you can see that there's already 2 cylinders that have been added to this rigid body over here. And indeed you can see there's the center of gravity and the rigid body frame. For the rigid body, these 2 cylinder features are added to. Use the visualizer to help get an intuitive sense of just what it means to adjust these angles. So if I change this on one of these cylinders to 45 degrees, you can see that it's tilted one of the cylinders a little bit. Move that back here. Maybe we make them a little bit further out, and we'll go +7 and -7, change the spacing. If you go to feature definition, right click on the hull, we can play with the amount of angular segments. Maybe we want to add a bit more definition so they're a little bit more of a cylinder, because that's what we want to do just in terms of exploring the effects of the mesh on the response. And again, remember, this is one rigid body system. So if we change the state even though these don't physically look connected, these are part of the rigid body, individual rigid body system. So if we go to the state of the rigid body, we can change the, if we move them offset in Y, it's moved them together as a system. If we give the whole system a pitch of, say, 15 degrees as its starting orientation, they all move together as a single system. So don't confuse the rigid body orientation and the feature frame orientations. The features are always fixed with respect to the rigid body. A common question is just how many panels do we really need in our cylinders, and to make sure we're accurately kind of getting an idea of the dynamics. The general idea is it's easy to go overboard, and a lot of people working with software like this the first time will add a lot of polygons, perhaps more than is necessary. This is probably okay. We probably could use fewer than this. One thing to point out is that Proteus will automatically detect polygons that are at the water surface and split them temporarily into an above water and below water component. So even though it looks like these cylinders are quite a bit more coarse than this, a lot of effects like buoyancy, the changing buoyancy and wave excitation and wind loading will actually be quite a lot more well distributed than initially it looks like. So that's a really good balance of computational performance. And the real answer to this is you need experience, and play with sensitivity studies with the software and see what happens when you do change the number of polygons, and see if you can tell yourself and judge for yourself how much of a difference it makes. But I would say, I would caution you not to put on too many to start with. Start off more coarse and then add detail later, I think, is a prudent way to go about things. Other features that we have in the software, cuboid, of course you can change the length and the height of these kinds of features. Ellipsoid, here it is in a sphere, but you can change the length one way or another to make different kind of ellipsoid shapes with the same sphere ellipsoid type feature. Custom meshes, you can create your own mesh as long as it's an OBJ file format and import it into the software. Usually this can take a fair amount of time to set up, but it's a good way to get information from a CAD model. You'll have to do some conditioning in another tool like perhaps Rhino 3D to get it to look nice, and not to have, you want to have nice kind of a distribution of elements that are roughly kind of the same size and aspect ratio, and there's some guidance on this in the manual on setting up a custom mesh. This is an example of a poor mesh, for example. There's really big elements on the sides and way too many elements on this area of curvature. It's just not going to resolve it's going to be way too computationally costly to run this, plus the distribution of hydrodynamic loading is going to be really poor, poorly resolved over this kind of hull. So just taking a file straight out of a CAD program is usually just never works out very well. If you do make a custom mesh, you need to do things like make sure the normals are pointing outwards, and you can check on this in post-PDS. Just quickly inspect the mesh and see if the normals are all pointing outwards. We have a relatively new video tutorial on configuring and adjusting a mesh from a CAD file as well. That would be worth checking out. Okay, now we're going to look at the other example, the EcoSpray platform. EcoSpray platform is a relatively small catamaran that was used to deploy and make measurements of flow and waves in a high flow tidal channel. And it has a drag plate to kind of adjust the loading on the mooring. And what the point of this is just to kind of show how many features can be used to make up a rigid body. So there's several custom meshes for the pontoons. Those probably could be reasonably well represented with cylinders too, but it's possible to add. I just want to point out that you can have combinations of custom meshes. There's a larger cuboid used for the deck, and many for the gantry frame here for the drag plate. And of course, if you go to look at the feature definitions for these, you can change the added mass coefficients, the drag coefficients for each of the components, the geometry for them. You can turn on and off different sources of loading. Wind loading, hydro loading is drag and added mass. Hydrostatic Frau-Krylov is buoyancy, and Frau-Krylov force is from the static pressure field and the dynamic pressure field when there's waves present. And again, some mesh parameters here. Right, so this might be nice to kind of play around with, just get a sense of like what it's like to work with these input files, and with a rigid body with a bit more complexity in the setup. Another option is a visualization mesh. Visualization meshes are often helpful to show interesting detail that is missing from hydrodynamic features. There is a feature visualization model. It has very similar inputs to the custom mesh model. You provide an OBJ file, but it doesn't use this OBJ file for any hydrodynamics calculations, which is nice. You don't have to really worry about the mesh quality, which is good, and just sometimes it's useful to show some information that's missing from the simplified hull models you're working with. So in review, we talked about mass properties, the crucial importance of the rigid body reference frame and how everything is specified with respects to that. The hydrodynamic features, we talked a lot about the different features available and how to work with them and how to configure them. All right, thanks for watching.